Hello, everybody. In this video, we will explore the different ways we measure distances in astronomy. As we know, we use different units to measure distances between objects on Earth. For example, to measure the distance I throw a football, we can use inches, feet, or yards, or meters or centimeters if you live outside the US. But if you want to measure the distance between cities like Beijing in China and Columbus in Ohio, using inches and feet or meters and centimeters will not make any sense. So it would be better to use other units like miles or kilometers. The same idea applies to distances between celestial objects. Using miles or kilometers might be enough to measure the distance between Earth and the Moon, but it becomes difficult to use these units to measure larger distances, such as distance between Earth and the Sun, or between the Sun and Proxima Centauri, which is the closest star to our solar system. To measure the distances between celestial bodies, we need different units of distance. For example, we know since the 1500s that Jupiter is about 5 times the distance between Earth and the Sun. This distance between Earth and the Sun is called the astronomical unit, or AU, and it is the standard unit of measure in the solar system. Once the AU was established, geometry was used to determine the distances between the Sun and all planets in the solar system. Jupiter, for example, is located 5.2 astronomical units from the Sun. Saturn's distance from the Sun is 9.5 AU, while Neptune is located 30.1 AU from the Sun. But for a long time, we didn't know the exact value of the AU in miles or kilometers, and could not calculate the distances between planets using these units. Astronomers tried different methods to calculate the value of the AU, including using the transit of planets like Mercury and Venus across the face of the Sun. But the values were not very accurate. Finally, in the 1960s, astronomers used radio telescopes to bounce radar pulses off of Venus and use the time it took for the light to get there and back to calculate the precise value of the AU, which is now 149,597,870.7 kilometers. The calculation of the AU value allows astronomers to predict the motions of planets, moons, comets, and asteroids, and to launch our probes into space and explore these celestial objects up close. To measure distances to objects outside the solar system, like to other stars in the Milky Way, astronomers combine the AU with parallax measurement. Parallax is the perceived shift of the position of an object farther away in relation to an object that is closer. The nearby star appears to shift in different times of the year in relation to the fixed stars in the background, which are farther away. One easy way to understand parallax is to stick out your thumb in front of you and look at a distant object with one eye at a time. It looks like your thumb has moved in relation to more distant objects in the background. The same idea applies when we look at the stars. But because the stars are much farther away, using just your arm is not enough to see a shift in the position of the star. In that case, we look at the shift in the star's apparent position at different times of the year, which provides a much larger baseline for parallax measurements, allowing us to measure the distance to nearby stars within our Milky Way galaxy. The amount of shift depends on the distance between your eyes and how far away the object is. If the object is nearby, the shift is large. The farther away the object is, the smaller the parallax shift. That creates a problem because distant stars might be too far away for parallax to be a reliable way of measuring. The angles will be too small. But because the stars in other galaxies are much farther away, soon the AU became too small to be a convenient unit, and another unit was needed. Astronomers began using the light year to measure distances to objects beyond the nearest stars. A light year is the distance light travels in 1 year. The light year is a measure of distance and not time. Light is very fast, and in 1 year, it can travel almost 6 trillion miles or over 9 trillion kilometers. But space is vast as well, and even at very high speeds, light still takes time to travel from one celestial object to another. For example, the distance to the moon is 1 light second. The moon is very close. But the distance to the nearest star, Proxima Centauri, is over 4 light years away. The distance across our galaxy, the Milky Way, is about 100,000 light years. The nearest galaxy to us, Andromeda, is about 2.5 million light years away. This graph shows the distance to some celestial objects and locations in light year. Another unit used to measure the vast distances in space is the parsec. A parsec is the distance from the sun to an object that has a 1 arcsecond parallax. The parsec is based on the angle a star shifts over the course of a year. A star 1 parsec away would have a parallax shift of 1 arcsecond. That distance turns out to be about 3.26 light years away. To measure distances beyond our galaxy, astronomers use a variety of other measurements. We will learn more about these measurements in Chapter 12. So in summary, we learned that different units are used to measure different types of distances. Because astronomical distances are too large, it is not practical to represent them using common units such as miles or kilometers. For a long time, astronomers tried to measure the precise distance between Earth and the Sun, also known as astronomical unit or AU. This value was finally calculated in the 1960s using radar pulses bouncing off the planet Venus. Astronomers use the AU to explore and understand the distances and motion of objects in the solar system. Using the AU in combination with parallax, they were able to measure distances to objects beyond the solar system and to nearby stars. Because the distances within and beyond our galaxy are too vast, 2 other distance measures, the light year and the parsec, are used. The light year is the distance the light travels in 1 year, and the parsec is the distance from the sun to an object that has a 1 arcsecond parallax. Thank you for watching, and I see you in the next video.